Welcome everyone to Season 2, Episode 1 of our Vulnerability Chaining Masterclass AI Security Edition. We are diving into the world of vulnerability chaining, how attackers link together seemingly small weaknesses to pull off major AI compromises. Throughout this talk, we'll explore how prompt injections, malicious inputs designed to manipulate a model's behavior, can open the door to sensitive information disclosure. Think of it as a chain reaction. A single prompt triggers a cascade of events that leads to data leaving your environment. Our goal isn't to instill fear, but awareness. By understanding how these chains form, we can learn how to break them. Before we begin, a quick but critical disclaimer. This episode is for educational and defensive purposes only. We're showing how these attacks work so that you can build better defenses, not to encourage misuse. Always obtain proper authorization when testing systems, follow responsible disclosure practices, and treat this knowledge as a tool for strengthening your organization's security posture. With that ethical framework in place, let's delve into the heart of the matter. So what exactly is vulnerability chaining? In AI systems, it's the practice of chaining together multiple low-severity vulnerabilities, such as minor prompt injections, to achieve a high-impact attack. Guardrails and static filters are bypassable, and complex RAG or agent pipelines create more hops where an attacker can nudge the system toward the data they want. The blast radius grows quickly because one compromised tool often unlocks entire data lakes or API access. Instead of thinking about single bugs, we need to think in flows, a chain starting with injection, moving through context misuse, and ending in data disclosure. Prompt injection is the gateway to system compromise. These attacks involve inputs that manipulate a model's behavior, overriding the developer's instructions. They work because large language models can't inherently distinguish between what the developer told them to do and what a user or attacker tells them. Direct attacks include role-playing jailbreaks like do anything now, adversarial suffixes that confuse alignment, or obfuscated prompts in other languages or encodings. Indirect attacks lurk in content the model processes, hidden text in documents, poisoned emails or web pages. Multimodal injections even embed instructions in images or audio. The key insight is that if the model can parse it, it can be exploited. Don't fall for the misconception that RAG or fine-tuning alone eliminates injection risk. According to the OWASP Top 10 for LLM applications, prompt injection is the top critical risk. Let's unpack those injection techniques. Direct attacks might involve elaborate jailbreak roleplays that coax the model into ignoring safety filters. Adversarial suffixes that appends gibberish to confuse alignment, or translating instructions into base 64 or low-resource languages to slip past English-centric filters. Indirect injections hide in the content your AI consumes. White font text in PDFs, instructions inside emails or web pages. Multimodal injections go even further, embedding hidden prompts within images or audio that a vision model obediently follows. The take-home message here is that any content, textual, visual, or audio, fetched by an AI pipeline is a potential attack vector. Attackers continuously innovate in these channels, so your defenses need to assume nothing is safe by default. Now we shift to the other end of the chain, data leakage. What kinds of information are attackers after? PII and customer records, names, emails, phone numbers, financial details, even health records. Secrets such as API keys, database credentials, and internal system passwords. Intellectual property like proprietary algorithms and confidential internal documents. There are model layer risks, verbatim memorization of exact training data and semantic memorization of sensitive logic. And application layer risks like misconfigured retrieval, RAG systems returning documents a user shouldn't see. Unsafe output handling that displays raw model output without redaction. And user-seeded leakage when the context window contains sensitive data. Critical assets at risk include the system prompts themselves, private RAG documents, customer data, and secrets. Understanding what's on the line underscores why attackers chain these vulnerabilities together. Let's walk through a typical exploit chain. First, the attacker injects a malicious prompt, seeding new instructions that override safety policies. Next comes abuse. The model ignores policy and invokes privileged tools or accesses restricted context. Then extraction. Sensitive data appears in the model's output, logs, or side channels. Finally, exfiltration. The attacker pulls that data out via URL fetches, image rendering, or API calls. From the attacker's perspective, they don't need direct database access. They just need to convince your AI to summarize the database for them. The critical failure is implicit trust in model output. Breaking the attack down further, the chain starts with reconnaissance, identifying chat interfaces, RAG sources, or upload endpoints. Then payload crafting, adversarial suffixes, hidden HTML or JSON injections. Execution bypasses controls. Tooling accesses plugins or data stores. Output renders raw sensitive information. Exfiltration steals the data. And finally, cover-up tries to blend traffic and evade logs. When you map it out this way, you can see how each step sets up the next. Digging deeper, here's the anatomy of an PI attack. Reconnaissance identifies inputs, chat interfaces, RAG sources, upload endpoints, or hidden prompts. Payload crafting uses adversarial suffixes, hidden HTML markdown, JSON field injections, or context overflow. Execution bypasses guardrails and forces routing. Tooling accesses plugins, queries databases, reads files, or makes API calls. Output renders raw sensitive information, embedded links, or hidden text. Exfiltration steals data via callbacks, image fetches, or side channels. Finally, cover-up attempts to evade logs by blending traffic and deleting history. Each phase sets up the next, and breaking any one link can disrupt the chain. As AI pipelines become more sophisticated, attackers adapt with multi-chain injections, nested Russian doll payloads that survive multiple passes through different components. Imagine a prompt that first bypasses the enrichment chain, then in test mode, forces routing to a vulnerable processing tool, and finally injects a hidden field that causes the summary to include a malicious markdown image URL. Attackers use tactics such as forcing routing to specific chains, injecting hidden JSON fields, or piggybacking on summary generation. The impacts are serious: arbitrary content generation, data exfiltration via markdown links, and cost blowups from long or looping outputs. The key mitigation is strict schema validation and field-level whitelisting at every hop. When each link in your chain rigorously validates inputs and outputs, nested payloads have nowhere to hide. Theory comes to life in the Samsung incident from early 2023. Engineers in the semiconductor division uploaded sensitive source code and meeting notes into ChatGPT to optimize code and summarize meetings. Because the service wasn't under enterprise control, that data became part of the model's retention history and potentially future training sets. Within 20 days, 3 separate leaks occurred. The root causes: shadow AI usage, employees using unapproved AI tools without security oversight, a lack of guardrails and data loss prevention systems, an unclear corporate policy on what data could be shared. Samsung's official ban came on May 2 after the leaks were discovered. The lesson is clear: treat public LLMs as third-party data processors. If you wouldn't email sensitive data to a stranger, don't paste it into ChatGPT. The Samsung example isn't isolated. According to recent reports, 77% of employees admit to sharing sensitive data with AI tools. Only 13% of organizations report known breaches, 8% are uncertain, and 79% believe they are secure. A gap that suggests many incidents go undetected. The human factors are telling. Convenience often outweighs security, and many users simply don't realize that public LLM inputs may be used for training. On the technical side, traditional data loss prevention tools struggle with context-heavy prompts, and security teams frequently lack visibility into what prompts are being sent to external AI APIs. Shadow AI, unapproved tools used outside official channels, amplifies exfiltration risk by a factor of 3, while the average cost of an AI-related data breach climbed to $4.45 million in 2024. This reality check underscores why robust governance and awareness are critical. From a business perspective, the stakes couldn't be higher. Financially, the average breach response costs $4.45 million, not counting token cost spikes from abusive loops or regulatory fines under GDPR or CCPA. Legally, unauthorized exposure of PII or IP can violate NDAs, trigger class action lawsuits, or run afoul of the EU AI Act. Brand-wise, trust erosion, viral screenshots of failures, and drops in market valuation are real risks. Operationally, AI incidents complicate incident response, cause downtime for retraining or patching, and burn out security teams. Shadow AI usage magnifies these problems. When leadership understands that vulnerabilities translate into costs, liabilities, and reputational damage, it becomes clear that AI security isn't just an IT concern, it's an executive priority. So what can we do? The first line of defense is at the perimeter. Input controls start with sanitizing and normalizing, strip invisible characters, enforce strict token and character limits, and block prompt injection delimiters like triple backticks. Detect jailbreak patterns with heuristic filters and specialized classifiers such as Llama Guard or Prompt Guard. Segregate untrusted content. Wrap external RAG data in tags that instruct the model to ignore embedded instructions. On the output side, enforce strict schemas and validate responses against expected formats. Redact PII and secrets with regex and NLP-based DLP scanners. Finally, apply the RAG triad verification. Check that responses are grounded in provided context, that the context is relevant, and that the answer actually addresses the query. These controls treat both inputs and outputs as untrusted until proven otherwise. Perimeter controls aren't enough. Deeper defenses matter too. Apply least privilege tokens so that summarizers can't write to the database, and never hardcode API keys or secrets in prompts. Introduce a human in the loop for high-impact actions, like sending emails or deleting data. Isolate critical logic from LLM processing. Separate chains, validate boundaries, and implement egress filters to block outbound connections to unknown domains. Monitoring closes the loop. create structured logs of inputs, outputs, and metadata, detect anomalies such as spikes in token usage or unusual patterns, and automatically rate limit or suspend abusive users. Defense in depth means combining these layers. No single control is sufficient. We are aiming not just to prevent attacks, but to contain them and detect them quickly. Stepping back, remember that prompt injection is rarely the attacker's end goal. It's the doorway to sensitive information disclosure. Minor injections become critical when chained because modern AI architectures employ multi-chain designs, enrichment, routing, and processing steps. Each handoff is a vulnerability if it lacks validation. There is no silver bullet. Robust defense requires schema enforcement, output reduction, least privilege access, and continuous monitoring. Implement controls at every hop: input, output, tool access, and data egress. The key takeaway is that breaking any link in the chain reduces risk, but only multiple layers working together provide resilient security. To translate strategy into action, here's a practical timeline. In the first 30 days, implement input validation on all prompts, add output sanitization to prevent data leakage, update system prompts with security instructions, and create block lists for known injection patterns. By 60 days, enforce least privilege access controls, deploy real-time monitoring for injection attempts, establish chain isolation boundaries, and build secure API gateways for LLM interactions. Within 90 days, conduct red team exercises against your LLM chains, implement automated vulnerability scanning, develop incident response playbooks, and integrate these measures with your broader enterprise security architecture. This phased approach ensures quick wins, tactical improvements, and strategic resilience. And that wraps up episode 1 of our AI Security Edition. We just walked through how prompt injection doesn't just break guardrails, it chains its way into full-blown data exfiltration attacks. In the next episode, we're taking this even further, stepping into a vulnerability most teams still overlook: how insecure LLM output handling can lead directly to XSS attacks. We'll break down real examples, payload construction, DOM manipulation risks, and the defensive strategies you need to deploy right now. If you're serious about mastering AI security and staying ahead of attackers, make sure you don't miss it. So, before you go, hit like, drop a comment with your thoughts, and subscribe to Bug Bounty and beyond. Turn on notifications so you're the first to catch episode 2 as soon as it drops. Thanks for watching, stay curious, stay secure. And I'll see you in the next episode.